engineering, a special interest. Okay.
Sorry, I just started recording the meeting, so it made a noise. Go ahead.
Okay.
Are you hearing me? Are you hearing me?
Yes, we can hear you. It's a little muffled.
Yes. My discipline is civil engineering. I first came across this summer school through a break, and though I didn't have much knowledge about oceanography because of the concrete structures that is having ability challenges when it is erected in ocean. And I feel that if I have understanding of oceanography, this may really assist me to in my study.
Olunade, it's a little bit difficult to hear you, but I think I heard that you're based in Nigeria. And
In my further research.
Sorry, it was a little bit challenging to hear you. But if you can type in the chat also, we can see.
You can see any questions you put there very clearly.
Looks like you're in a car.
And that would apply too for anybody else that feels more comfortable putting questions in the chat. Feel free to do so. We will make sure we monitor the chat, and we will make sure we try to answer the questions, or at least explain why we're failing to.
So I think let's have the final two people introduce themselves, and then we'll start with questions. And then if anybody else joins, we'll give them a chance to introduce themselves. So it looks like Dr. Sumit.
Hi, hello. Hello, am I audible?
Yes, we can hear you.
Yeah, myself, Dr. Sumit from India, Presidency University, Kolkata. So we are working at Sundarban Estuarine System, the world's largest mangrove ecosystem in India. So already my student, I think she introduced herself. So we have just started our work in ocean acidification. We are still, it's infancy basically. So this workshop we joined to gain some knowledge and pursue our future research on these aspects. So we are mostly interested to work on the impact of synergistic impact, basically the ocean acidification and global warming, all combined effect on physiological energetics of some estuarine animals. So I guess this session will be helpful for us, and we'll get more knowledge from the experts like Professor Christopher Sabine and Professor Dickson. So thank you very much for giving us the opportunity to this platform. Thank you.
Thank you, and I encourage you to join Sam DuPont's lecture or discussion tomorrow. He'll be talking specifically about ecosystems and species. So if you're interested in more of the physiological or biological aspects, he'll be leading that discussion.
We are in contact with Sam, and actually this workshop, summer school, Sam only told us to participate.
Oh, great! So
we didn't know earlier about this summer school. And we are grateful to Sam for telling us this about this summer school.
Great.
Thank you. Thank you for your.
So let's just do a couple more introductions, and then I'd like to go on to questions. So Olahide, if you want to introduce yourself.
Yeah. Good day, Alexis. How are you today? I'm Olajide Joseph from Nigeria. I'm an undergraduate of the Federal University of Technology, Akure, Ondo State here in Nigeria. I'm a marine science student, pretty much interested in ocean acidification, and I'm liking this topic about carbon chemistry. I have a couple of questions to ask. I would so much like, if I'm given the privilege, to ask questions when it's time. Thanks so much.
Thank you.
You're welcome.
You're muted, Alex.
I muted myself, sorry. I think there's more and more people joining all of the time. So why don't we begin with questions, and we'll take moments to, you know, ask people to introduce themselves. Andrew and Chris, how would you like to do this? Would you like people to, you know, unmute themselves or type in the chat box to ask, or do you want to call on people?
I think it would be easiest at first if, you know, if people would, there's the opportunity on Zoom to raise a hand, which I'm searching for now, but I know it exists. But basically, if that would be the easiest, because then we would see who was specifically requesting.
On the menu bar on the bottom, there's a button with reactions. Oh no, that's, you do a thumbs up there.
You know, I think you can just use the check mark.
If
just
you
use
go
the
to,
yes.
you know, realistically, if you open up the participants, then you click on participants, a little window comes up with the names of everybody. And there's a menu bar under there with like a green check mark and red check mark, et cetera, et cetera. Under more, there's the possibility, I think, of putting a symbol. But either way, if you do that, a symbol appears by your name in that list. And like Christopher just put up a hand, or put a hand there.
So just really put anything up next to your name.
Yeah,
like this,
that would do it. Otherwise, obviously, if it's silent, interrupting silence is fine. But if there's more than one person wanting to ask a question, that would help it order, because the system orders it automatically. Again, as we noted, if you put it in the chat box, we will also include those in a timely fashion. So the choices are yours.
So we welcome your questions.
The option is open.
Good day,
Yeah, maybe I should.
Andrew. Hello.
Should I come up first?
Sure, please.
I'm not seeing where to raise the hand.
Yes,
okay,
please.
I'm not seeing where to raise the hand. Okay. Yeah, my question is really concerning the solubility of carbon dioxide in the surface ocean. Because why I'm asking this is I'm having a problem with trying to explain decreasing temperature with the decreasing of the PCO2, the surface PCO2. Because most times I try to say, okay, the decreasing of the surface PCO2 is due to the temperature decreasing. I will have comments like, it is not correct. I will have comments that it's not really correct, that if I say the cooling of the surface ocean absorbs more carbon dioxide, then how do I say that the PCO2 is decreasing with decreasing temperature?
I think
so. I have not really gotten that very clear.
So,
and
Margaret,
I'll be appreciative if you really give me a clear picture of it, please.
Sure. My picture of that is you draw a distinction between two different ways of imagining what is really happening. The first one is imagine that the seawater sample is in a completely closed container. It cannot gain or lose CO2 to anything outside it. If it has a particular temperature and composition, it will have a particular PCO2 associated with that water. If you change the temperature of the water, then all the equilibrium constants change their values. And a consequence of this is that the PCO2 becomes smaller. Now, what we've really said is actually that the solubility of CO2 increased when you decreased the temperature.
Temperature, yeah.
And you kind of know that with all the bottles of champagne you've never drunk, because people cool it to keep the bubbles in. And so cold drinks with lots of carbon dioxide in don't fizz quite as quickly or as much, losing the carbon dioxide, as when they're warmer. So cold it's more soluble. It's a lower PCO2 if you didn't change the composition. So now we come to the next system, which is really what we normally think about, which is a glass of liquid or an ocean of liquid. It's got the liquid that we just talked about, but it's also got this interface to a gas phase, the atmosphere. And we say, okay, what is it that makes this different? And one thing that makes it different is carbon dioxide can go backwards and forwards across that interface.
Yeah.
And the real change there is that what makes it go backwards and forwards? Well, it always goes backwards and forwards. But if the two parts are what we call at solubility equilibrium, then the same amount leaves the liquid as goes into the liquid in some finite time. Seconds, let's think of it. But if they're not in solubility equilibrium, then we have one of two choices. You could gain CO2 from the atmosphere, or you could lose CO2 to the atmosphere.
To the atmosphere, yes.
You gain CO2 from the atmosphere when the PCO2 in your liquid phase, the solution, is less than the PCO2 in the atmosphere.
Yes.
You lose to the atmosphere when in the liquid phase it is more than it is in the atmosphere. My example with solar would be that that's the case. A lot of CO2 dissolved. When it was under pressure and cold, it was in solution. When you've dropped the pressure and you've started to heat it up, it comes out of solution. And so, yes, when you cool the ocean, because cooling happens much more quickly than the transfer of carbon dioxide, instantaneously you do drop the PCO2 at the surface. But if it was previously in equilibrium with the atmosphere, a rare but occasional phenomenon, then that lower PCO2 means it now starts to gain CO2 from the atmosphere because you've made it a little more soluble in that particular composition of water. At that position, composition and temperature.
Okay.
So I hope that helps to clarify it for you.
So just as a reference, when you change the temperature, the CO2 changes by about a little over 4% per degree. Yeah. The PCO2 changes by about 4% per degree Celsius change.
Mm-hmm. Yeah.
For those of you that have thought about this, there is one added confusion, which is if you change the PCO2 in the atmosphere, in actual fact, more will go into the warm water than goes into the cold water. But that's largely because of other changes as well in the oceans and is an added confusion. So there is some confusion about discussing this completely clearly and unambiguously.
Okay, maybe that is the confusion that is really overwhelming me, because I see if along a transit going towards maybe the ice, you are seeing a decreasing temperature, and also you are seeing a decreasing PCO2. You try to say that it is because of the decreasing temperature, then you are asked to actually look at other dynamics. Maybe that is what you are trying to say.
I think, yeah, that's a third case that I didn't even bring in, which is if you actually change the composition of the water you're looking at, as well as the temperature, which is what happens when the ship goes to a different region. It's a different temperature, but the water also has a different composition. And that, of course, complicates everything. My example was for the very simple system of having the same composition of solution, but changing the temperature.
Okay.
So when you start to go on a ship's transect, it's convenient to remember that the PCO2 does change with temperature, but it's not always the whole story. There are all the other pieces that come in that will ultimately affect what the PCO2 value is in that water. And the composition is also a dominant piece.
For example, if your ship were to move into an area of higher productivity, the phytoplankton in the water can draw down the CO2. That has nothing to do with temperature.
The temperature, yes. Yeah, I know that.
If it's in a region where cold, high CO2 water is upwelled, the temperature will go down, but the PCO2 goes up. So when you start to think about changing the composition, that is not a separate issue, that's a combined issue with thinking about temperature.
So at that point, what do you say about the DIC? That is when you have when you have upwelling and the temperature decreases, but you are having something like outgassing. So what do you say about the DIC?
Well, that upwelled water is also higher in DIC, right? So remember, most of the carbon, the inorganic carbon, is stored in the form of bicarbonate.
Yes.
And so that's that reserve. When you change the temperature of the water, you're converting between the carbonate, the bicarbonate, and the CO2 species. Most of that carbon is in the form of bicarbonate.
Mm-hmm.
So that's your reserve of carbon it's drawing on to change the PCO2 if you're just looking at PCO2. That's a small fraction of the total amount of inorganic carbon. So if you want to be, if you want to remove the temperature effects directly, you can look at DIC, because DIC is not directly a function of temperature. If you take Andrew's case where you have a parcel of water that's isolated from anything else, if you change the temperature, you will change the PCO2, but you will not change the DIC, because the total amount of carbon is fixed, right? You're changing the ratio of the bicarbonate and the carbonate and the PCO2, but you're not changing the total CO2 in that case, or the DIC.
Oh, okay.
So in many ways, it's easier to think about DIC as a tracer in the ocean.
It's certainly true that the DIC is the thing that changes most cleanly and clearly with changes in the carbonate system due to things growing, due to mixing, due to gas exchange. It's an easy one to understand that you either add some or you lose some.
Yes.
But it's complicated by another piece, which is that there's another factor about seawater, the alkalinity. And in a simple surface water where things grow, using up CO2, they use up CO2 much more quickly than they change the alkalinity. They do change the alkalinity a little bit because of nutrient uptake, but it's much more quickly. And so what's really happening is the ratio between the DIC and the alkalinity is being changed. And the PCO2 is dependent much more closely on that ratio than on one or the other. And so when you get upwelled water mixing, exactly what really is happening depends on how much it's also changing the alkalinity. Typically, again, the DIC in deeper water has grown more relative to the surface water than the alkalinity has grown. And so you start off that water, if brought to the surface and not losing any CO2, would have almost invariably a higher PCO2 than you had originally, particularly if you brought it up to normal surface water temperature in that region. But it's complicated. The exact amounts depend much more on that ratio than on either one. The broad direction depends substantially on the total carbon because, on the whole, changes in total carbon are larger than changes in alkalinity. So it is the bigger factor.
Thank you. Yeah. Thank you so much.
I just want to note that we do have an opportunity for people to apply for one-on-one coaching sessions where it's really, you'll have an opportunity to speak to either Andrew or Chris or one of our other trainers in depth about your work. So there's an application in the Slack and Brian is going to email that out later today.
Okay.
But I think
Olajide
had a question, is that right? I think.
And also Dr. Sumit did.
Okay.
Hello.
So are you going to be?
Yeah.
Alexis, we will leave you as handing out questions.
I have one question to both experts. That how vulnerable is the estuarine system compared to coastal waters or the open oceanic water in the due to this emission of greenhouse gases, carbon dioxide? And another question is how vulnerable the freshwater ecosystem also compared to marine ecosystem in due to this CO2 acidification.
So probably Chris knows a lot more, but let me throw in my brief opinion. Number one, the word vulnerable is more, it doesn't really convey very much. What you're, I hope, or think then when you say that is it will have implications for the organisms and ecosystems in that environment. And if those are bad, good, or simply a change is what we would need to know, because vulnerable suggests it was bad. Estuaries clearly, like any other water body exposed to the atmosphere, is going to increase in its average CO2 level by trying to stay in equilibrium with the changing atmosphere. And that too would be true for fresh waters. And in the marine science environment, a significant number of organisms don't seem to clearly respond to the change in total carbon that happened. Rather, they're influenced by some other piece of the acid-base chemistry. For instance, if they are calcifying organisms, changing the carbonate ion concentration influences them. Changing the hydrogen ion concentration, the pH, also influences some organisms that have been studied. Changing the dissolved unionized CO2 concentration affects photosynthesizers. So to make a real statement broadly about this requires trying to work out which of these really matters and how much it happens. But most broadly in estuaries and freshwaters, there's less, the chemical word that's usually used, but it's not always very clear, is buffering. That is, because there's less alkalinity, as well as less total CO2 in many environments, their resistance to change, that is, for every change in the atmospheric concentration, how much does the water really change in composition, is not the same in all those places. And you'd need to think what's really changing and what are the ecosystems that are of interest to you, either because of their intrinsic charm or their economic importance.
Andrew, I think they might have also asked about variability in the different systems. Is that right?
Well, the phrase that was used is how much is coming in from the atmosphere. We can now, of course, come on to making it a lot more complicated, which is that estuaries and freshwater systems are awfully near where man has other immediate and direct effects on the composition of the water that affect the carbon chemistry, such as adding fertilizers by accident, which then encourages things to grow, which changes the carbon chemistry, or adding organic compounds that decompose with microbial action, changing the carbon chemistry, or just polluting with an acid runoff. So there are so many other ways that are much more important to the changes in freshwater and estuarine environments than present day transfer of CO2 from the atmosphere. Chris? More?
Professor Andrew, do you think that humic acid in estuarine ecosystem has some other role rather than CO2 alone in buffering the system? So what is the role of this humic acid? Because in estuarine system, we can see that due to the litter fall, lots of humic acids are forming in the system. So how can you...
Clearly, they play a role in the acid-base chemistry, a very difficult to characterize role. The other speculative possibility is they also complex trace metals, which may reduce the implications of those trace metals for organisms in ways that are much harder to understand and follow. And the extent to which they do that is probably also affected by changes in the acid-base chemistry. So it's a messy system. There's a lot to be said for not touching estuaries. Having started there as a postdoc, I learned that the hard way.
I want to make sure we get to everyone with questions. So I've got a few people queued up. So first is Olajide. And then just so you know, everyone, I'm telling everyone in the chat what order. So it'll be Olajide, then Falilu, then Sritama, and then Abraham. So Olajide.
Okay.
Yeah, Andrew Dickson, there's a question I would like to ask, and there are two. Of recent, my lecturer asked a question in class, which none of us was able to answer. He said,
"You need me to do your homework?"
What did he say?
I said, "You need me to do your homework?" I asked,
Not
yes,
homework.
I will answer your question, of course.
not homework, Andrew. He said in photosynthesis, if oxygen was not present, how will photosynthesis That was the question he asked.
Forgive me, your voice faded out after the words, if oxygen was not present. Could you please repeat it?
Okay, my lecturer asked the question in class and he said, in photosynthesis, if oxygen was to be absent, how will photosynthesis continue? Okay. That was the question he had. Fine. Yes, that was the question.
So the way that I would view that question, whether or not this is what he was looking for, it probably is. Photosynthesis means you're taking energy from light.
Yes.
And you're using it to reduce carbon dioxide to lower oxidation states, which are what you have in the various organic molecules that you are synthesizing. However, to do that as a chemical process, you have to oxidize something else at the same time. Normally, we take the water and produce oxygen. And that's the reaction that's taking the that the electrons are coming from, basically, to do this. So you need some other redox system to supply the electrons instead of water. And the result would be an oxidized form of that particular redox system would need to be produced in order that you have the ability to use the energy from the light and reduce carbon dioxide, which is an oxidized form of carbon +4 oxidation state, to organic compounds, which tend to be, 1 to -4, depending upon exactly what they really are. Methane -4, formaldehyde 0. These are formal oxidation states for the carbon, but the key is you had to reduce the carbon dioxide, and those electrons had to come from somewhere.
So where are the electrons coming from, and how will the equation be balanced?
Once you decide where the electrons are coming from, balancing the equation is relatively trivial. But where the electrons come from is largely a matter of a convenient environment to do this, where things can come into contact with each other. And that's not as easy for many things as it would be for putting an aqueous system there, i.e. having water there. So I would suspect, to the extent it does happen in various places, it's different depending upon the microcommunities that are doing it, because it will take very different enzyme systems to achieve this. But you are now dredging way beyond my knowledge of biochemistry.
Okay, please, I have one other question to ask. He said further, the present day anthropogenic activities has actually increased the rate of CO2 in the atmosphere. And he said this CO2 are actually going into the ocean, which make the ocean more heavier these days, making it unable to accept some other gases. Now, he asked us to look for something which I don't even know how to go about it. He mentioned something about F factor, telling us to solve for the F factor, whatever, of the carbon dioxide and carbon monoxide, telling us the F factor will be given 0.003 thereabout, if I'm right. Do you have any idea about that?
No, sadly, using the letter F for factor is not a particularly sufficient information to decide what you're talking about. There's a variety of pieces that exist. One question is, of all the carbon dioxide that goes into the atmosphere, how much ends up in the ocean or how much stays in the atmosphere? Stays in the atmosphere can be broadly treated as a fairly constant factor, but whether you'd call it F or not, I don't know. Another is in the oceans itself, when organisms are taking up carbon dioxide and photosynthesizing, and a significant proportion of that organic material is ultimately sinking out of the lit mixed layer deeper into the ocean, you're asking, well, what proportion of the total production was doing that? And that is sometimes used as an F, I do know. And so there's a variety of these, and without knowing exactly what you were talking about, it's hard to help you here. I'm sorry.
Okay.
Thanks, Olajide. And feel free to add more questions in the chat. But let's go ahead and move on to the next person, who was Falelu. So Falilu will be next, and then Shritama, Abraham, and Michael. So if you want to be added to the list, either raise your hands or type in the chat. So Falilu, you feel free to unmute yourself.
Yeah, can you hear me now?
Yes.
Can you hear me? Okay.
Yes, can hear you.
Yeah, thank you. My question is really my question really borders around something that when I go home, when I travel back, get back from my office, passing through the lagoon system here in Lagos. It's a major lagoon system, the Lagos Lagoon. I have been working on the open ocean, the coastal ocean carbonate chemistry. But what my question is that how does the fluctuation, because in the lagoon system, it has a kind of a semi-diurnal tidal system, whereby you have the influx of the sea and the influx like twice in a day. That's two high tide and two low tide. So, and on a diurnal basis, the salinity varies the salinity of the lagoon system varies. So my question is that how does this salinity variation, how does it impact on the carbonic chemistry of the lagoon system and the near adjacent coastal water? How does it impact on the carbonate system? Because the salinity sometimes drops as low as, depending on the season anyway, it could drop as low as maybe 15 or even less.
So it's obviously the salinity is changing because you've got a different proportions of freshwater input and saltwater input, depending upon the state of the tide and the state of the rain. But when you change the salinity, you're changing the background ionic composition, which changes the values of the equilibrium constants in the carbonate system. So changing the salinity tends to change the proportions of the various carbon species, carbonate, bicarbonate, CO2, in reasonably predictable fashion. Of course, in the system you're articulating where it's diurnal and reasonably shallow by the sound of it, temperature is also changing at the same time and possibly loosely correlated with the changes in salinity, but also reflecting the time of day, which is not correlated with the time of the high and low tides because those change position through the month. So you have to think about both parts. How is the temperature changing? How is the salinity changing? But the other real complexity you've got is what you're really seeing in that water also substantially depends on the composition it had as it was added to the lagoon and anything else that is added while it is in the lagoon. And the most likely source while it is in the lagoon is coming out of the bottom, the sediment, pore water, things there from microbial decomposition of organic material. And with a tidal system, you've got an interesting feature, which is that the sediment doesn't move around very much. I mean, it does, obviously, you can probably see that, but it isn't following the water. And the water comes in and out on the tide substantially. And so what ultimately really matters for it is saying, what is my water composition? And is there a way I can think about it to understand why it is that composition now? Because that allows you better to judge how it might have varied in the past and how it might change in the future and what the implications of this would be for any ecosystems that you are of interest to you in that area. But I mentioned earlier the desire to avoid looking at estuaries, and what you're really talking about is a a somewhat geographically unusual looking estuary, because you've got both freshwater input and tidal saline input. But because it's a lagoon with limited mixing, it probably also has substantial input from the sediments in there as well, which complicate very much understanding how this evolves in time and season. Though in Lagos, the season is probably more dominated by rainfall than by striking temperature changes.
Yeah, good. Yeah, well, then one other thing again is that which means by what you're saying now is that there seems to be kind of the changes in salinity, the input of freshwater and input somehow complicates the carbonate dynamics. Is that what you're trying to emphasize?
Well, what I'm saying is that realistically, you can only tell what's happening by making regular measurements. But because these results are changing depending upon other factors, whereas with the ocean, there are lots of places we go, oh, we measured it this, and 3 years later, it probably won't be very different because that part of the ocean is broadly the same for a large distance around. We're deep enough that it's not being changed very much, even by annual productivity cycles in the surface. And so the convenience is you don't need so many measurements to get the picture. In your system, you need many more to start to get a picture. And balancing how well you get that picture and how expensive it is to study it is one of the hardest parts.
Okay, just lastly, then.
Oh, sorry, Valauri, I just want to invite Chris also to jump in.
Oh, okay.
Because we also have Chris Sabine on the line.
Okay.
I guess I would just add that you need to think too about the composition of the river. If you've got such low salinity, you probably have rivers flowing into that estuary. And you can think of it as a mixing process of ocean waters that have a particular carbon chemistry and fresh waters that have a different carbon chemistry. And as the tides go in and out, you're having different ratios of that ocean water and the fresh water, the river water, that are mixing and combining. And then you add that third component that Andrew mentioned of the sediment fluxes. You need to understand all of the different in members that are contributing, that are all mixing together in that estuary to form the carbonate chemistry of the waters in the lagoon or in the estuary.
All right. Yeah, I was just to ask now concerning the measurement now for the carbonate chemistry. I want to find out that for this kind of estuarine system, the standard measurement, the standard method for measuring the carbonate chemistry, will it still be applicable in this kind of system? Is this still applicable to this kind of estuarine system, as against what we have in the open ocean system?
My comment there would be, yes, very applicable at salinities above 5. As you go to that region where it really has a significant input from the river part and the salinities are lower and lower, then only some of the methods still work well, and others are much harder to see as a logical continuation of what you were seeing for the oceanic. pH is the most striking. The way people would measure pH in freshwater is significantly different from the way marine scientists measure it in the open ocean. And those two have not been carefully joined and showed that the join actually helped you understand the CO2 system.
All right. So which means if I were to if I were to design, for instance, for the Lagos Lagoon system, now, if I were to design looking at the dynamics of the carbonate system, it means that I would rather have to limit my my measurement to a level whereby the salinity is at maybe 5% minimum.
5
maximum
parts per thousand.
Yeah. Sorry, part per thousand rather. Sorry. So it means I will have to limit my salinity to 5 parts per thousand in order to be able to characterize how the carbonate system varies in the system, maybe relative to the adjacent ocean.
Well, not quite. I mean, my comment meant that from 5 up, the methods work pretty well exactly the way you would have expected. If there's the same amount of things you're measuring, then they work equally well. But if it's lower amounts, you typically always get a noisier measurement expressed as an amount by measuring less of it because other problems grow. But Chris's point, which is understanding how the freshwater input affects your system, is still important. But that has to be done at the level of things that mix sensibly. So really, you there would be measuring alkalinity and total carbon. And for freshwaters, those measurements work probably almost as well as they do in seawater. The alkalinity is less precise in freshwater, typically. But it can be measured reasonably well. And so you do need that. And so you can't ignore the really low end. But I just warn you that to get the best measurement quality, you need to be aware that it's harder to make the measurements in that low salinity region.
Right, so just to kind of build on that a little bit, one of the things we do as carbon chemists is we know that if we measure 2 carbon parameters, we can calculate all of the others, right?
Yeah.
That works well. We have a certain set of equations and constants that allow us to do that in seawater.
Yeah.
But the relationships, we make some assumptions and some shortcuts in seawater that don't necessarily apply in freshwater. So one might need to use different constants and equations in freshwater. When you get into a mixing zone, as Andrew's talking about, where you've got, you know, a salinity of 5 to 20, where you're mixing the freshwater and the saltwater, where do you move from your saltwater equations to your freshwater equations is a bit complicated. Kind of a simple way to think about it.
Yeah.
I just, for the interest of time, I'm going to keep moving along, but Falalu, if you have additional questions, you can always type them in the chat. But again, to everyone, we are offering applications for coaching where you'll have an extended period of time just with you and some experts. And so,
sorry, Alex. Sorry,
ahead.
Alexis. Is it possible to get the transcript? Can I get the transcript?
Yeah, so I'll post the recording to the Slack channel so that everybody can see it.
Great, thank you.
Yeah, so I think just so everyone knows, the order is going to be Sritama, and then Abraham, Michael, and then Clement. Okay, so Sritama first.
Okay, so I have a question. We all know about a program, Excel program, that is CO2sys. And it is widely used to calculate the carbon chemistry of seawater. And I was I came across a lot of literature, scientific literature, which uses this software, this program, to calculate the carbonate chemistry in laboratory experiments in enclosed system. So is it feasible to use the same program for a closed and laboratory experiment? Actually, I don't know if it is designed only for the open oceans or it can be used in lab experiments as well. So that is my question.
That program and many others like it simply aim to do the calculation for, when the calculation is done, it's assuming it is a closed system. If you want to use that information to handle an open system, then you need it in some other, embedded in some other thing. Because the thing about an open system is you are changing let's say for seawater, either the total carbon or the alkalinity or both. And although you may not have measured any of those, you might be measuring, let's say, pH or PCO2 or both. It's the changing composition that matters. And so when you do a CO2 cis or any of the other calculations, you're doing it for one composition only at that time. You can have in CO2 cis the ability to put in multiple compositions, but they're each handled individually in the calculation. And as a result, how you use multiple calculations to think of a process is up to you. The software doesn't care. Its assumption is at each time it is doing a single calculation for a single composition of solution with the known temperature and pressure.
I would also add that CO2 cis, I mentioned previously that there are shortcuts that we take in calculating the distribution of the different species. CO2 cis makes those shortcuts. So and it assumes that you have seawater type compositions of other elements, right? So for example, the boron concentration affects alkalinity, and that affects our calculations. CO2 cis assumes that you can get the boron concentration from salinity, which because it's the constancy of composition of seawater. So it assumes that you've got seawater distribution of all the different elements in seawater. So if you're doing calculations using artificial seawater, where you don't necessarily have all of the same components, then CO2 cis may introduce errors into your calculations.
Yeah, I mean, essentially what Chris is saying, to put it into the context that I used, I said you were doing it for a particular composition. And when I say that, I'm actually generalizing that concept. So that's all the things that are present in that solution. And as he points out, to do that, you need to know, at the very least, equilibrium constants, and preferably also total concentrations for every acid-base species you wish to consider. And CO2 cis does assume that the only ones that really change are the CO2 environment, or phosphate, or silicate, or maybe ammonia. I think there are versions with that in as well. Hydrogen sulfide. But they don't change the one that typically doesn't change in marine systems, which is the one that Chris mentioned. And for all that, the word composition, the real assumption we're making is that the word composition can be handled for a lot of these purposes by the alternate salinity, which is telling us not only that the composition, it's all the other ions, which is what affects the equilibrium constants, but also the total concentrations of species like boron, fluorine, or sulfur. Tells us what their composition and things are assumed, and that's assumed for it being seawater.
But if you were to do a lab experiment where you just put sodium chloride into distilled water or deionized water, it's not going to be the same as if you had started with seawater.
Yeah. So what those bring to you is two conveniences, and you have to be aware that one of those conveniences is potentially problematic. The conveniences it brings is it does do the calculations straightforwardly and correctly. The problem is that the things it uses to do that calculation are not completely flexible. It makes choices as to what constants you could ever put in there. There are a selection of them, but by no means is that everything you might have. It assumes that you're interested in something that has a completely seawater composition, and that there are no other acid-base systems present. In a lab experiment, any or all of these can be modified to suit your taste, as Chris made the point. And so that part of it falls apart. My own recommendation would be, for that kind of lab experiment, you need to do your own calculations, but you can test that you program them correctly by putting in the plain seawater assumptions and comparing it to the answers you get with CO2 cis.
Let's go ahead and move on to the next question. Thanks for Tama. I think that was a really good question. Abraham is next, and then it'll be Michael and then Clement. So Abraham?
All right, good afternoon, everybody. Can you hear me?
Abraham, could you talk a little bit louder? I'm not hearing you very clearly.
Okay, I said.
Much better.
Good afternoon, everyone. Can you hear me?
Yes.
Okay, thank you very much, Prof. Okay, I'm Dr. Ibrahim Ekberisi from the Nigerian Maritime University, Department of Marine Environment and Pollution Control. My research background is in pollution studies and remediation. I think I came late because I was in the other lecture that had to do with Professor Samuel, who was giving us a historical perspective on research and science. Thank you very much, Prof. I've gone through the videos you sent earlier, and I want to thank you for a very good job on both videos. And also to Professor Christopher, I've also gone through yours too. Thank you very much, because I've been reading a lot for the past, I think, a month plus or two about ocean acidification, and the videos have really given me the fundamental concepts, you know, the ideas about it. Although I'm not, I think the chemistry is a bit, it's a bit kind of complex for me, but I know I have to go through the videos on I think go through it over again before I can really fully say, okay, I have a firm understanding of many of the things you are saying. Okay, but so far, my own aspect is that how do we move forward? Because I've read a lot, downloaded the software, but how do we start? And looking from your video, that's like 2011, and some of the equipment are very, very expensive. I don't know, are there digital device or handheld device that we can carry to the field to start measurements? And you know, even how do we get crashed to it, or even start citizen science of ocean acidification? Because what I'm asking, the Nigerian Maritime University is on an island in Delta State. We're surrounded by seawater, and a few kilometers away, it empties into the Atlantic Ocean. And to the best of my knowledge, we started like 2 years ago, the first maritime university.
Excuse me, you just seem to be moving away from your microphone. Could you keep closer?
Oh, sorry about that. Okay, I don't know if you
about
heard
your island. How it was surrounded,
yes,
and it faded away there.
Yes, that the university is on an island that is surrounded by seawater or salt water that empties into the Atlantic Ocean a few kilometers from us. So my point is, how do we really start? Because I've read a lot of things. So how do we start? How do we move from this theory into the practice of I know at first it may not be accurate. A lot of errors may emanate from our studies and all that. But how do we start? And what are the basic tools we need to start? Thank you.
Well, I'll give a very quick answer, but then let Chris and maybe Alexis talk. Essentially, you have to decide why you even want to start. Are you interested in understanding the health of a particular ecosystem and how it might change under such circumstances? In which case, a lot of your guidance is likely to come from the kinds of information that Professor Dupont has been talking about.
Okay.
Or are you also ready, thinking, okay, we need to study the CO2 chemistry to help others who are studying the ecosystems, in which case you're right. The problem is that the easiest information to find is that from rich countries who have relatively straightforward access to whatever equipment they think they need. The word expensive is completely a relative one. I think it's fair to say that in my own country here in the US, the equipment used to measure CO2 is not considered expensive by most modern day chemists. It is expensive to our biologists, and it's undoubtedly even more expensive in many places. And so there is an effort going on, and Chris Sabine has been working on this quite a bit, to try and get simpler, cheaper methods to be equally well documented. And this has been done, encouraged by Alexis at the Ocean Foundation. Those sadly are still, I feel, in their early days, but it does potentially give you a start to be aware of them, and they can make you more aware of them.
Right.
Yeah.
So
go ahead, Chris. Sorry.
No, go ahead, Alexis.
Oh, I think that's true. And I also I put something in the chat that on Friday, there's actually going to be a whole session just about kind of monitoring OA and how you would get started. And tomorrow there's a session with Dr. Sam DuPont on studying it. So many more opportunities to learn about this. And then, yeah, so that's all I wanted to say. Chris, why don't you go ahead?
Okay. Well, yeah. So I was just going to say that Andrew, Alexis, and I have been working through the GOON project, which is a global ocean observing network, and developing a set of lower cost equipment that can be used to measure alkalinity and pH in the oceans. And we're happy to share the list of equipment that you can buy and how you would put that together. And we have developed training videos, and we actually do on-site training workshops all around the world.
At least did in the good old days.
Yeah, that's right. Back when we could actually interact with people, we would do workshops to teach people how to put together and run the equipment. But we're happy to share any of that information. And one thing to consider is, you know, the first step in understanding how ocean acidification might be changing in your particular area is to get baseline measurements and at least understand the current distribution of the carbon species. So one of the things we promote is, you know, starting with a monitoring program where you can begin to document changes in your particular area, because no matter where you go in the global oceans, the ocean acidification is not the same everywhere. And so documenting the changes in your particular area can be quite useful to the global community in terms of understanding the variability in different regions.
Yeah, and I posted the, oh, sorry, go ahead.
Okay, I think that's very true. I want to agree with you because, you know, I was thinking about it. One of the things I intend to do is that, because I know there are a few research on water quality that had to do with brackish water area. You know, I told myself that, okay, at some point I'm going to do a review to see if they have, some of those research has a pH measurement and maybe carbon measurement and stuff like that. Okay, I said, okay, at some point I'm going to do a review, because other than that, I don't think there is really ocean acidification or PCO2 measurements, like monitoring baseline data available. So I said, okay, but I'm going to do, looking at the angle for people that are doing a benthic.
Sorry, it's a little hard to hear you again. Can you raise your microphone again?
Oh, sorry, okay. Okay, I said, okay, looking from the perspective of those doing benthic studies, water quality studies, I could just, you know, try to gather data relating to pH and maybe dissolved carbon, and that will also kind of sort of be baseline data before starting the monitoring program. I think that's also part of what I want to do. And also, I think recently I joined the Global Ocean Acidification Observing Network, where Natalie Monashi has been assisting me with some resources. Although her lab has not been on because of COVID-19, if not, she promised that, okay, that she will help me too with some of the videos from her lab. So if there are videos in that network too, I really appreciate getting them, and hopefully I look up to the presentation tomorrow and next tomorrow that may talk on the effect on maybe the ecosystem and the carciferous organism and some other related subjects. Thank you.
Yeah, I'm just going to respond to Abraham, but this goes to everyone. So like Andrew and Chris mentioned, at the Ocean Foundation, we've got a program that's really trying to lower the cost of monitoring and get equipment into the hands of scientists. And so if you you can contact me if you want more information about this, but basically Chris and Andrew have really been the scientific leads on designing these lower cost systems, and they're designed to be pretty easy to fix and pretty easy to operate, but they give you high quality data. So there's videos that will be online soon. The videographer is just finishing it up right now. They told me it should be done within the next few weeks. And these videos show you how to measure alkalinity on a system that Andrew designed. It's just essentially a titration. And then also how to measure pH using a spectrophotometer. As well as how to collect bottle samples properly. And Chris is the guide in all of these videos, walking you through all of the steps. And if there are any colleagues from French or Portuguese speaking places, that will also have subtitles in French, Spanish, and Portuguese. So that will be available soon, but in the meantime, please feel free to contact me for more information. And I also recommend going to the Go On website. I posted the link in the chat. There's some really great resources there. One of the things is called the peer-to-peer network. And I know some of you are part of that, but this is a really good opportunity to sign up to receive a mentor, usually a scientist who's been working on this topic for quite some time, and they can help you develop your research program. And there's also a scholarship program that the Ocean Foundation runs specifically for the peer-to-peer program. I know Falilu has been supported with this before, and this allows you to maybe purchase some equipment or in normal times travel to receive some training or have somebody travel to your lab. So, if you want any more information about any of these, please, I'll put my email address in the chat box, but and then the other place that I would recommend, which I think Abraham you posted on, is the Ocean Acidification Information Exchange. It's a forum that is just for basically asking questions and sharing information. And so I'm going to post the link to that as well. And this is a really nice way to connect with many, many people all over the world who are studying this issue, and to learn about events and trainings, and also to ask questions.
Okay, thank you very much. I think I'll be contacting you a lot, and the videos will be very, very helpful. I think we look forward to having those videos.
Yeah.
And perhaps the device that they are building as well. Thank you very much.
So I'm going to call on Michael next, and then Clement. So Michael first.
Good afternoon, everybody. Good afternoon. Can you hear me?
Hi. Yes, I can hear you.
Okay. Good afternoon, sir. Good afternoon to the entire team. I'm very impressed, and I'm happy to be in this forum. I and Abraham and I are from the same university. but I'm in the Department of Marine Geology. And so we also do a lot of chemical oceanography and physical oceanography. But I'm a petroleum geologist and a sedimentologist. But I took interest in this because of my department, and being a senior person in the department, I have to have a hand-on about all this that you have been teaching us. And so, because another thing is that the area where our university is, like Abraham told you, is on an island opening into the Atlantic Ocean. And the amount of pollution is terrible. I learned a word from Chris, pentagram. I don't know when he was discussing the amount of carbon that enters the ocean. He puts into consideration pollution by burst pipes, illegal activities, and so a lot of us are very concerned, and we want to research into it. Number one, to help the environment, about diversity, and people who live there. They kill, they feed from fish that survive this terrible environment. They even sell it to the public, and we don't know what's happening. So it's a concerted effort to see what we can do to help the marine environment and the communities around that place. So that is why a lot of us are very interested. So my knowledge of the chemistry behind the acidification is still at the elementary level. But simple question I want to ask is, when crude petroleum goes into the water, is the carbon immediately available to the environment? I need to know that so that we can now have a picture of what is going on. So that's one aspect. So then I'm happy you talked about the equipment, because we really need affordable equipment as a third world country that we can purchase. I happen to be head of department, and we are going to be submitting lists to procure equipment. So it would be nice for us to have this so that we can procure some of this equipment and delve into research that will be meaningful to Nigeria and meaningful to the entire world. Because like Chris said, no matter where you are, you impact on the global environment. So that's my little contribution and question, sir. Thank you. Hello.
Chris, did you want to answer the one about the petroleum?
Sorry, everybody. Can I just add something to what Dr. Mike said?
Of course.
Okay, I think what he also didn't mention is that because there are petroleum industrial activities there is a lot of gas flaring sites as well, and
yes.
we understand from our little knowledge that gas flaring results in acid rain and stuff like that. So all through the entire mangrove in that axis, there's this consign, though we've not done a lot of research about it, that be accelerating the results of, the rate of acidification within that axis. So I don't know if you can also throw light on that as well. Thank you.
Right, so that one's a little more straightforward. The gas flaring, of course, produces CO2 in the atmosphere, and where you have locally higher atmospheric CO2, that will of course drive a net flux of CO2 into the oceans. However, the atmosphere is generally well mixed, and those CO2 concentrations get blown away by the local winds. And I think that local effect is not as great as you might expect, but of course that contributes to the global increase in CO2. Regarding other oil spills or petrochemicals that are put directly in the ocean, I guess I mean, I think there are a few microorganisms that can metabolize petroleum products, but not a lot to my knowledge. Perhaps Andrew knows differently. But what I would think would be potentially a bigger effect would be the impact of that pollution on the biological cycles in that region. That if that pollution then, you know, kills off particular ecosystems or species, that's going to have a dramatic impact on the carbon cycling in the region. I don't know, Andrew, do you have other thoughts on this?
Yeah, I mean, there's no question, of course, that pollution from spills of crude oil are problematic for many, many ecosystems, particularly in coastal regions where it lands on the surface of everything. In the open ocean, there's less obviously done, but people have been following, you know, after the big disaster that happened in the Gulf of Mexico a number of years ago, when a platform completely caught fire, and then huge amounts of crude oil were pumped into the ocean for protracted periods of time. And it was apparent that a significant amount of that oil ultimately was biodegraded by microorganisms. And of course, when that happens, you've got two potential contributions to what we're talking about. One is you're increasing the dissolved CO2 level, because when they degrade it, one of the products ultimately is going to be CO2, if there's enough oxygen there to permit that. And on the other hand, crude oil has huge amounts, by comparison with refined oils, of nitrogen oxides and sulfur and other things in there. And so these two contribute to the acid-base chemistry, I suspect, as they're released into seawater. But the details of this, I'm not aware of anybody studying from the point of view of what are the implications for the acid-base chemistry. Much more studying for how quickly is it disappearing, and thus what are the likely longer-term implications to the environment of what's there.
Yeah, it really is very dependent on the location. There was an interesting study comparing that spill that Andrew mentioned in the Gulf of Mexico, where much of the oil was metabolized, versus the Valdez spill in Alaska in the United States, where that oil was not metabolized. And the difference seems to be the fact that the Gulf of Mexico has a lot of natural oil seeps. And so for hundreds of years, oil has been leaking into the Gulf of Mexico waters, so there are whole ecosystems that have evolved around that, and the microbes were in the area ready to metabolize that oil. You don't have that in the Prince William Sound, where the spill was in Alaska. So it really depends on the availability of those microbes and whether they're naturally occurring in that region as to whether that oil gets metabolized quickly or not.
Thank you. Thank you. It's clear. So that leaves a lot of work for us to do. We need to find out whether those microbes are available in the environment, and whether the action of pollution acidifies our local environment as well.
Yeah, look at the publications from the Deepwater Horizon spill. Those were the studies that showed the microbes metabolizing the petroleum.
Okay. All right. Thank you, sir.
Thank you. I know Clements has a question. So Clements, if you want to ask your question now, and then after that, I think we'll just have kind of an open floor for a new round of questions. So Clement. wonder if he lost, oh, he's online. So you're muted, Clement.
His picture seems to be frozen.
He might be
Hello.
reconnecting. Oh,
Hello.
hi.
Hello. Hello.
We did hear you say hello, Clement. So please speak
Hello.
more, but it's not a good line.
Hello. Sorry, my network is very bad. Hello, can you hear me?
Yes,
we can hear you. Yes.
Hello, can you hear me?
Yes, we can hear you.
Hello.
Go ahead, please.
Clement?
Go ahead.
Okay.
We can hear you.
Okay, thank you. Thank you so much. Okay, thank you so much for the opportunity, and I'm very happy. I'm learning a lot from this program this year. Well, I have a degree in biological science, and I'm now looking for specialization in perhaps fish gear technology. But I really want to ask simple question. Since I'm a fisherman, I grew up on the coast, and more than 15 years now, I've been on the coast fishing. So one thing is that the question is, you see, sometimes we move on the water, and then we are talking about the dissolution of carbon dioxide, especially carbon dioxide in the water. I want to know that the water itself is having a pressure, and then there's a pressure in the atmosphere. And sometimes we do move on the water surfaces, and I want to know how the composition of, especially this CO2, will be in the water since the pressure is increased or decreased. I just want to know the relation. Thank you. Hello.
So I'm not completely, this is Andrew answering.
Hello?
I'm not completely clear in my mind what you asked, but I think I know. Essentially, there's a potential. Clement, I think you're having trouble with your sound. I will answer your question, but realistically, you may need to come back and listen to the recording to get a better hearing of it. Essentially, the confusion is there's a term we call partial pressure, which refers really to a gas in a composition in a gas phase.
Sorry, I have a bad network, that's why.
And the partial pressure is an equation that's a product of the mole fraction in the gas phase and the total pressure. And when we talk about the partial pressure of CO2 in seawater, we say what we really should say, but we're too lazy, is the partial pressure of CO2 in a gas phase that is in equilibrium with a particular sample of seawater. And we just say, PCO2 seawater. So when you change the PCO2 in the seawater, then you are changing how it will interact with the gas phase. But if you also change the total pressure of the gas phase, you change how it interacts with the seawater. So if you double the pressure of the gas phase, then indeed you would have doubled the PCO2 in the air, even though you did not change the composition of the gas phase. And so the way it interacts with the seawater is it would be a different equilibrium. And so the complexity is both these can matter. And you need to be clear when you're thinking about this, which one you are thinking about. Partial pressure, which is a way of thinking about the composition of a gas phase, but we make it a convenience for looking at the level of unionized CO2 present in the seawater. or the total pressure, which also affects the partial pressure of a gas in a gas phase, but doesn't hardly at all over small changes of pressure, like doubling it, change what's going on in the seawater. So the hard part is you just need to have it quite clear in your own mind before you can really sort out what other people are saying who are not being quite so scrupulous with their language when they talk about it.
I would also add that the way I think about it is carbon is stored, inorganic carbon is stored in the ocean in the form of DIC, dissolved inorganic carbon, right? So it's not just the partial pressure of the CO2, but it's also the bicarbonate and carbonate ions. All of those together form the inorganic carbon system in seawater. But what controls the exchange of CO2 between the ocean and the atmosphere is just that partial pressure, right? So the uptake of CO2 by the oceans from the atmosphere is controlled by the difference in the partial pressure. Wherever the pressure is highest, it wants to be in equilibrium. So if you increase the CO2 in the atmosphere so that it's higher than the partial pressure in the water, then the CO2 is naturally going to move from the atmosphere into the ocean. Or conversely, if you have some process that increases the partial pressure of CO2 in the seawater so that it's higher than the atmosphere, then the ocean is going to lose CO2 to the atmosphere because it always wants to be in equilibrium. But that's only a fraction of the CO2 in the seawater. Most of the carbon is stored in the form of bicarbonate. So there's all these different equations, but the exchange is based just on the PCO2 difference, and the storage is based on all these other species that also form when you add CO2 to seawater.
Clement, if you want to type in the chat any follow-up questions you have, that might be the easiest way, given that there's a delay in the sound. If anybody else has any questions, great, I saw your thumbs up, Clement. If anyone else has any questions, I welcome you to either raise your hands using one of the features in Zoom, or type in the chat. If you can't see the chat, or you can't see the button to press, now there's no questions queued up. So this is a time when you could also just ask a question.
And I would just point out for the number of people that have joined us more recently that Alexis is recording this and will make it available through the Slack channel appropriate to this. So if any questions that you've missed, you do get the chance to go back and hear them should you wish.
Okay, thank you.
Okay.
So as Alexis said, we're open again for questions.
Olajide has a question. Is there any PDF material available for more understanding? He typed it in the chat.
Yes. Obviously, the question really that's perhaps relevant is, what are you hoping to understand? Because the ocean acidification has a number of separate organizations that play a significant role in communicating broadly. One of these we've mentioned already was the Global Ocean Acidification Observing Network, and their website has some things that you will find useful to improving your understanding in this area. There's also the ocean acidification office run from Monaco that has put out a couple of manuals, one of them being a guide to doing ocean acidification, which is a series of separate chapters written by different scientists a number of years ago, but still, and some of it has been modernized, but still providing quite a lot of information. Some of the methodology exists. I was involved with Chris Sabine in writing a handbook about CO2 measurements and that has appeared and has been translated into a number of languages in whole and in parts. And those are available through our own NOAA website. So there's a variety of these websites out there that have various PDF material that almost certainly you could find to be helpful. However, they do have the complexity that was raised earlier, which is that on the whole, such things were written by scientists like myself and Chris, who are fortunate enough to work and live in wealthy environments. And thus, the access worldwide to the kinds of equipment we talk about and the methodologies we choose to employ is not so good. And Alexis is working through the Ocean Foundation, and also Goan is working to try and address that and rethink how many things can be done very successfully with much less resources, but still absolutely relying on the key resource, which is the skills and interest of the person doing it. And that's why you're here. You have those skills and interests, and you're looking to improve the skills perhaps more. So these things exist, and you could put together that kind of a list in the Slack channel later that would help people to find more of the online stuff that does exist in this area already.
I've added a link into the Zoom chat to the guide to best practices for ocean acidification that Andrew mentioned earlier. So you can look at that. There's also this new question, do you expect OA in the Atlantic Ocean in West Africa? And to that, I would say that ocean acidification is a global phenomenon. It's happening everywhere as we burn fossil fuels and increase the CO2 concentrations in the atmosphere. There is a natural process for that CO2 to move into the ocean waters, and that will result in changes in the carbonate chemistry that ultimately lead to ocean acidification. So our best understanding is that ocean acidification is a global phenomenon that's happening everywhere. What we're finding, though, is that the levels of ocean acidification, the magnitude of the change is very dependent on local factors. And there are, particularly in coastal waters, processes that can exacerbate the ocean acidification effects, or in some cases ameliorate the effects. And we end up with both hotspots and ocean acidification refuges. And that's where a lot of the current research is moving right now, is to better understand what are the rates of change in one location versus another. I'm located in Hawaii, and I've got 4 different moorings located around the particular island of Oahu that I'm on. And just within a few kilometers, there are huge differences between the rates of change, say in Kaneohe Bay on the windward side of Oahu versus the rates of change on the south shore of Oahu. So it's very important, if you want to understand ocean acidification, to look at your particular environment, get a baseline, and then understand the processes that might be affecting ocean acidification in your area. And of course, the other issue with ocean acidification that makes it interesting but also more complicated is it involves basically all of the different disciplines of oceanography, right? So it's ultimately a chemistry problem because the CO2 effect on the pH of the ocean and the saturation state of the waters is a geochemical issue. But the magnitude of the change is frequently affected by ocean circulation or other physical processes that are going on. And our real reason for wanting to study and understand ocean acidification is because of its effect on the fish and our ecosystem structure. So there's a biological component. And in my case, in Hawaii, we're very concerned about the effect of ocean acidification on the reefs. So that's a benthic and has a geological component too. So there are aspects of ocean acidification that involve biology, chemistry, ocean physics, and geology that we're trying to understand. So certainly the ocean acidification is something that everyone should be interested in studying and trying to better understand. But it's difficult for me to say in Hawaii what the impact might be in West Africa exactly. That's why we need you all.
Yeah, I think just stressing the importance of local data, and I think, you know, we'll talk about this, I think, a little bit more on Friday if you're in that session, but, you know, how do you start monitoring and where should you start monitoring, and should you pick a more pristine area? You know, we've had lots of discussions with people. If it's the very first measurements you're taking on your coast, it's very overwhelming to decide where you should be taking those measurements. So we have some suggestions we'll talk about on Friday about, you know, if you have access to a sensor, that's really nice because you can get high resolution. You can really see, you know, the changes over the course of a day, and you can maybe deploy that sensor in a few different places to understand the variability if you really don't know anything. And then maybe once you've done that, you can design a sampling program where you know how many samples you should be collecting and how often, because you know roughly how variable the area is. So I think truly, you know, we have some great global ocean data, in large part thanks to people like Chris and Andrew, but we're really missing, I mean, I feel like in West Africa, there's almost no coastal data. And so we really want to help you establish monitoring or experiments. And so, yeah, that's why it's so hard for us to say what's happening in West Africa right now, for sure. We have about 10 more minutes or so left in our discussion time. So if there's anyone who hasn't had a chance to ask a question, please feel free to either type it into the chat box or unmute yourself.
I'm raising my hand.
Yes.
Go ahead, Margaret.
Yeah, okay. I thought, yeah, I'm just excited with what Alexis just said about helping us in the West Africa to start up something about monitoring in ocean acidification. That would be a very good one for those of us, especially as we complete like myself, as I complete my my PhD and go back home. I'm a lecturer back home. At least I will have something doing after my PhD. Yeah, so I'm so excited. But I don't know, I just want to share a screen here if it's possible for us to see what the question I was trying to ask in the beginning, and
Go
see
ahead.
how, can I share a screen, please?
I believe so, yes.
Okay.
You may have to give her permission, Andrew.
I think I did.
Okay, let me see how, can you see it? Can you see my screen now?
No.
Huh?
Not yet.
Okay.
Not yet.
Not yet. Not yet.
What about now?
No. So,
Oh.
is there
Okay.
a green arrow that says share screen?
Wait.
There, now, yes.
It's coming on.
Are you there now?
Yes, we can see your screen.
Okay. Yeah, it's a PDF, not a PowerPoint. It's converted from, so you
I'm
can see in
not.
the
What we can see at the moment is actually a copy of a directory on your computer. So go back.
We're seeing your desktop.
Stop sharing, go back again, and a window will come up with different choices. Choose the one that looks most like the PDF you're trying to find.
Okay, let me see. Where am I now? I don't know again what's happening. Oops. I think I've mixed it, or what?
Yeah, if you've got too many things open on your computer, it becomes confusing as to exactly what gets shared. Sorry, Margaret. You're still showing your desktop.
Okay. It's like I'm getting it.
Rest assured,
There's
after
a
the
problem.
first few hundred times, this problem goes away. I've done that to many of my classes where I've shown them the wrong thing or nothing. Believe that nevertheless they're seeing what I was planning for them to see.
I'm afraid I'm not seeing anything again.
No, it's basically if you don't have that open recently, for some reason Zoom doesn't always seem to find it.
No, it has been open. I just opened it now.
So if you click on share screen, you should get a window with multiple possible choices that you could click on.
Like I'm not even seeing the page again, the Zoom page again.
Okay, for that you have to go back to Zoom, which means making sure that that is now your front program. It's problematic to do this remotely without practice, and even do it then.
Margaret, you know what? You can share this PDF in the Slack if you want, and follow up. I welcome everybody to use the Ocean Acidification channel on the COESSING Slack, and please feel free to add follow-up questions there.
Okay.
And there are more trainers who will also be able to answer your questions in addition to Chris and Andrew.
Okay, maybe that's what I'll do, because it's like I've missed it up all.
If you go to the very bottom of your screen, click on the blue icon with the little white camera in it, and that should bring up.
I'm clicking it. It's not coming up. I don't know where it has disappeared to. Actually, I'm using two screens.
Taufik Okunsai also put a question saying, what are the prospects in studying physical oceanography, especially ocean modeling? And Chris just pointed out that ocean acidification takes all kinds, because what really controls the chemistry is what is the composition of the water. And physical oceanography is one of the larger contributors to changing and modifying the composition of the water by mixing the oceans or waters in that region, one with another. So without understanding that mixing, it's hard to fully understand what really is influencing the effect. He pointed out that although the atmosphere is broadly behaving the same everywhere in the world, the mixing in the ocean environment is not. And as a result, what you see is a combination of both processes. So finally, we have the success.
You have the screen now.
So I hope that helps you, Taufik.
Yeah. Okay, so are we there now?
Yes.
Are we seeing it, please? Yeah. So my question was coming from this second column. That is the B, E, and H and K. This is the Astrid Ridge region in the Southern Ocean, close to the Antarctica. Here. So we can see the temperature, which is the blue one now, is decreasing. We have a decreasing temperature. I mean, yeah, the black, decreasing temperature and salinity. And we have the oxygen saturation increasing and decreasing, and PCO2 decreasing. So here I said that the decreasing temperature is most likely the reason why we have a decreasing FCO2, which I supported also with the oxygen saturation, which is also decreasing. Now I'm talking about solubility due to cooling. So the question I was being asked is, if I'm talking about solubility due to cooling, I should have more of the carbon dioxide being absorbed. So why should I be saying that the SST is decreasing, so we have the FCO2 decreasing? That is why I was raising up that question. And like we're talking about other dynamics, I should have said maybe the chlorophyll, maybe there's a photosynthesis going on here, but we can see that the chlorophyll concentration is lower here than even the other parts. So that is my confusion why I asked the question. So I just thought I should share the screen so that you can see it and maybe you can reason with me. Yeah.
That,
Want to try, Chris?
That middle plot, the B, E, H, K, those are...
Yeah, this second column, yeah.
That's longitude. Because
Yeah, it's along the longitude. It's along the longitude. It's just by the Antarctic coast, close to the Astrid Ridge. We have the Astrid Ridge around this area.
Because my first reaction in seeing those plots is that you must have crossed a front, or what it looks like is you cross some sort of a front on the right-hand side there, because you see that the temperature decreases, the salinity changes, everything is changing there rather dramatically, and that's very typical of crossing
a front
or perhaps a boundary current. And the challenge there is when you do cross a front or go into a boundary current, you can have quite different chemistry of the waters, because you can't just assume that it's the same water masses that you're seeing. So it could be that you're crossing into very different waters there that would...
Yeah, this is within the Weddell-Gea, just around like 60 south, or 60, I think 67 south. Yeah,
right.
Yeah, around the Weddell-Gea. So I'm not sure we have any front here, except maybe like you say current.
Right. Well, clearly something is changing, because you've got that dramatic drop in salinity and temperature.
Yeah,
temperature,
I mean, the word front is specific, but clearly if the salinity is changing like that and the temperature is changing like that, almost certainly this water, and yet we're staying at the same latitude, almost certainly this is a different composition of water to the water before, where the water to the left of that change is a different composition to the water to the right of that change.
To the right.
Right.
And
therefore you can't assume the carbon chemistry is...
We're getting mixing. between those, hence the word front, which is the area where it would mix. But what that means is that realistically, any discussion of how PCO2 changes is not purely due to one thing.
Right.
It's due to the composition of the water, which looks like it's a mixing between two other waters. It's due to any gas exchange that has occurred. It's due to any biology that has occurred. Unfortunately, all of these happen at different rates.
Yes.
So making a comment at one moment, I cooled it, the PCO2 went down. If you cooled a particular composition without changing its composition, that is not gaining or losing CO2 or changing the alkalinity, then yes, the PCO2 will go down. But if you made it colder by mixing in something that was colder with a lot more CO2, the PCO2 would go up. And so you can't say anything without recognizing that you've changed the composition of the water, and you have to untangle that piece out before you can look back at the other parts, like the biology affecting it or the gas exchange affecting it.
Right, because those changes could have happened elsewhere where you didn't make the measurements and were just physically transported to that location. So it's hard to know just from that one set of measurements to know what processes might have impacted the waters that you're mixing in.
So now how could you suggest one to decouple, maybe if you really want to know, because this is all about knowing the drivers. So if you really want to know the drivers here, what could you suggest? A way of decoupling it, something, I don't know how to put it, but how could you be able to, like, this process I'm using now, I'm using like a model of oxygen and carbon dioxide saturation to be able to determine the drivers. But here, like here now, we are expecting this particular region to be a heating or cooling region, but at the same time, we are seeing some biology and other remineralization. So how would you suggest that one can really decouple or be able to say, to show the processes going on? That's actually my concern now. What do you think I can do to be able to?
So what you're loosely saying is, how do you do all of oceanography?
You said?
It's a very large problem. You're asking about things, because what we'd say is, okay, oxygen, CO2, well, those clearly couple biologically, but they also couple with gas exchange. So we need to start to wonder about the relative importance of biology and gas exchange. But then the salinity changed as well. So that says that the water's not the same. And maybe it's not the same carbon to alkalinity ratio either. And so suddenly you go, oh, I need to know the mixing. I need to know the gas exchange. I need to know the biology, which means I need to do everything I need to do, everything on this to start to untangle it. So I think the right phrase is, yes, you always will have trouble. Because if this is the only information you have, you almost certainly don't have enough. If this is going to guide you to get additional information, yes. And if you wish simply to make up a simple story that one could tell that says, if this is happening, it would kind of look like this. Maybe you could do that too, but it doesn't say that that really is true without additional information.
So one thing you can say though is that you most likely have different waters that are mixing together, and you may not know the processes that ultimately led to the distribution of the different species within those waters, but you can say this is an area. So what I would probably do here is start first with a temperature versus salinity plot, and then see if you can identify different end members that might be mixing and kind of build a story based around this mixing of the different waters as a way of describing what's going on, rather than ultimately trying to get at, like Andrew said, I don't think you have enough information to understand fully the drivers that ultimately led to the concentrations you're seeing. Now, you might be able to do that more on the left side, where you've got some wiggles in CO2 and oxygen, where you've got relatively consistent temperatures and salinities. Now those you could start to look at and understand what's causing those little wiggles. But that big downturn at the right, I think, is pretty clearly a mixing of different waters that it's going to be difficult to tease out exactly what the drivers were.
Yeah, and
without
unless
having
you
more
know
information.
the original compositions of the waters that mixed, it's hard to go beyond that and say what other CO2 you gained or lost due to biology or gas exchange.
But if you do a temperature salinity plot and pick out the corners, then you'll be able to see where the different water masses are.
And if you know
the corners as what, please? Corners?
So,
what do you mean by corners?
So if you plot temperature versus salinity, if you have, if everything is a single water mass, then you would have basically a dot. Everything would be centered around a dot. What's more likely is it creates a line, right? And so where you've got two different water masses mixing, you're going to have a line between that connects one end member, which is one corner, and another end member. If you have three end members, you can make a little triangle potentially. But wherever you have the corners, those are the pure properties of the waters that are mixing. And then anything in between is a mixing of those two end member properties. Do you understand what I'm saying?
Yeah, I think I'm getting you. So just temperature versus salinity. So the points where we have like separation.
Right. So temperature and salinity are both conservative properties. So if you plot them against each other, they will show you where you've got different water masses, mixing of different water properties.
Okay, so you, because of the like a line of two different ends.
Yes, that if you have a line, then that's a mixing of two different water properties. The end of one line of your line is one, and the other end of the line is the other, and everything in between is a mixing of those two. Now sometimes it's not as clean as a simple two end member. You can have multiple waters that are mixing, but in this case it looks like you might be able to so what I would expect to see with a temperature salinity plot here is a whole bunch of points that all cluster in one spot. That would be all those waters on the left. And then you're going to have another cluster of cold, low salinity water that shows up in a different spot. And then you're going to have some data points that connect the big cluster and the smaller cluster. And that's your mixing line.
Okay.
So just a reminder to everyone that this this isn't your only chance to ask questions, and we do welcome you to join the other sessions that are on slightly different topics on Wednesday and Friday. But also, please use the Slack channel to ask questions.
Wednesday.
Sorry?
Today was Wednesday. I think you mean Thursday.
Oh, I meant Thursday.
Friday.
I'm sorry. I'm so off on it. You know, these days I never know what day of the week it is.
This is still March the 213th.
Exactly. Sorry, Thursday with Sam DuPont and Friday with Sophie Chu and Burke Hales. But like I said, this is not the only chance to ask questions. So I think we're gonna wrap up this live session, but I really wanna thank Andrew and Chris for all their time. And Chris woke up super early to be here live with us in Hawaii. And I also want to thank everybody who joined us and for your really excellent questions. We're really happy that you're interested in this topic, and we would like to help you explore it more.
Thank you so much. Thank you very much.
It was good meeting all of you.
Thank you. Thank you. We appreciate your patience.
Thank you so much.
And efforts.
I appreciate you.
Thank you so much.
Thank you all.
Thank you, thank you, Dickson and Christopher. Thank you so much.
You're welcome.
Bye.
Yeah.
Thank you all.
Thank you. Bye.
Take care.
Thank you, Alexis.
Yes. Yeah.
All right, I'm going back to bed. Good night.
All right.
Hey, it must be almost breakfast time by now, Chris.
It is. It's 7 a.m. It's time for breakfast now.
Uh-oh.
Yeah, the tricky thing, do you power through and go to bed early, or do you take a nap? It's always hard to decide.
I always vote for the nap.
Yeah.
Yeah, whether or not he got up early.
Well,
Or maybe I'm echoing my own thoughts.
no, I understand too. And it's only 10 for us. Anyway, thank you all so much. I'm gonna head out, but you have my email address. A funding opportunity. Oh, that's a good question. I think that the peer-to-peer scholarship is something we always try and make available. So we always try and have funding there, at least from the perspective of the Ocean Foundation. There's small grants that are given to people who are part of that network. So first you have to join the peer-to-peer network. There may be an future opportunities in West Africa specifically, but I need to get funding first, and then I can help distribute that funding out. You know, I think regionally, sometimes there are organizations like in East Africa, WIOMSA has provided some funding support for this type of work. So I'm not sure if there's a similar organization in West Africa that might be helpful. But maybe we can use the Slack channel to discuss potential funding opportunities. But that's all I can think of at the moment. Is the peer-to-peer scholarship is a good small grant fund to get started. And hopefully we'll be able to offer some larger programs in the future in West Africa.
That would be nice.
All right, thank you all so much.
Great, thank you.
We'll talk
Bye.
to you via Slack. Take care.